Namaste. Myself, Dr. Nagraj, working in the Department of Physics, Vadodara Institute of Technology, Hospete. Today, I am going to discuss about the concepts of optical fibers like attenuation and its causes, expression for attenuation coefficient, applications of optical fibers, and one of the very basic of application which we have here as point-to-point communication system. And finally, I shall be discussing about advantages and disadvantages of optical communication systems. Beginning with attenuation, here, whenever we are using the optical fibers for the communication systems, we are sending or transmitting the optical signals from one end to the another end. If I want to have all the optical signals which are being sent through the transmission line to be received at the receiving end, right? There must not be any loss. There must not be any loss of optical signals or the power, right? If, say, for example, if I am having the 10 optical signals have been sent from the transmission line, I must receive all the 10 optical signals at the receiving end. That's my target. That's my intention, the purpose. If there is some loss of power, it may be in the later stages we will be discussing by what cases the causes for attenuations are concerned. So if any loss of an optical signal is occurred, right, here this loss of power suffered by an optical signal as it propagates, as it travels through the optical fiber is known as attenuation. Here we have several causes for attenuations. Attenuation in the sense is a loss of optical signal. Right. Whenever the optical signal travels or transmits to the optical fiber over a longer distance. Now, when I look at the causes of attenuation, the reasons, and what might be the reasons not to have the attenuation or the loss of optical signal, there are basically three mechanisms which we have classified through which the attenuation can happen, can take place. One of the first cause here is absorption losses, and the second will be referred as scattering losses, and the third is radiation losses. At the first stage where we have the absorption losses, here the optical fibers are made up of with different kinds of materials. Right? If the optical fiber has some of the impurities present within the core material, and say for example, I do not know what type of materials which we use to construct, to design the core or cladding materials. Right? Say for example, if the core material has certain impurities present over, right? So if there are certain impurities like iron, cobalt, so several like metals or the elements, if they are present within the core material, these optical signals, which when they are entering in the core material, have its own energy. When that amount of energy is getting absorbed by the impurities present within the core material, hence these elements, the electrons of such elements will get excited to the higher energy levels. Again, they come back to the ground state with the emission of photons or energy. So those photons which have been emitted during their transitions is of no use. Hence it becomes a loss. One of the optical signal, when it is absorbed by one element, and that element will utilize that amount of energy for its transitions. During transitions, again, it may emit few certain amount of energies in terms of radiations. That energy will be of no use. Hence, it becomes a loss. Here we have observed during signal propagation, when photons interact with these impurities, the electrons absorb the photons and get excited to the higher energy level. Later, these electrons give up their energy by coming down to the ground state. And whenever they come down to the ground state, whatever the energy which has been released will be of no use. Hence, it becomes a loss. So hence we say this is a loss which has been observed due to the absorption of impurities. Right. And the second one is scattering losses. These scattering losses occurs due to the structural inhomogeneities, structural variations. Whenever while the signal travels in the fiber, the photons may be scattered because of sharp changes in the refractive index values inside the fiber. So say for example, if there is a change, if there is a variation in the refractive index of the core material, which might have been happened during the construction or designing of an optical fiber, whenever there is a change in the refractive index, we have observed that an incident ray will obviously deviate its direction, and that incident optical signal may escape from an optical fiber, and hence it becomes a loss. This type of scattering is also known as Rayleigh scattering. Whenever the light travels through a medium having the scattering object, these are the scattering objects we say. But here we have an incident optical signal. Here there is a change in the refractive index. Hence, this optical signal will get deviated its direction and may escape from an optical fiber. When these are the scattered photons, we say, when this is our scattering center. Fine. Hence, it becomes a loss. Only few optical signals will going to travel through an optical fiber. Right? And such types of losses due to the scattering centers, due to the scattering of photons will be known as scattering losses. And the third one, it may occur due to the radiation losses. The radiative losses occur due to two kinds of bendings which we observed during the construction part of an optical fiber. One such is macroscopic bands and another is microscopic bands. In the macroscopic bands, we have, this is a structure which we observe in the macroscopic bands, which may uh, arise during the construction of an optical fiber. Whenever an incident optical signal incidents in a core medium, and to propagate over a longer distance, it has to suffer total internal reflection. Fine. Whenever there is a larger bend, if it is observed, so from that end, the incident optical signal may escape from an optical fiber. Hence, it becomes a loss. That's what we have written. These are the bends with radii much larger compared to the fiber diameter. These bends occur while wrapping the fiber on a turning it around a corner. And hence, this optical signal suffers a loss. The energy of this optical signal will never be used, as since it will not undergo total internal reflection. Right? And another one is microscopic bends. These types of bends occurs due to the non-uniformities which is observed in the manufacturing of a fiber. As you can observe here, there are certain sharp edges. Sharp edges have been observed during the construction part. Whenever an optical signal incidents in an optical fiber, and whenever it incidents at the sharp edges of an optical fiber, then it may escape from an optical fiber. Right? Hence, it becomes a loss. Right? So here we have the micro bends cause irregular reflections, and some of them leak through the fiber. Here what we have written, rays escaping from a fiber. When these rays escape from an optical fiber, they becomes a loss. Some amount of energy of the signal has been lost during the transmission of an optical signals through the optical fiber, and due to the microscopic bends. Right? And what would be the parameter? What would be the attenuation coefficient? Right. So if I want to know how much percentage of loss that has been occurred or suffered by an optical signal as it propagates through the optical fiber, right? Here we have a parameter known as attenuation coefficient, denoted as alpha. Here, one of the scientists by the name Lambert, through his hypothesis, through his theory, he has explained regarding the attenuation coefficient. He says that the rate of decrease in the power of an optical signal is directly proportional to the initial intensity of an optical signal. And as an optical signal propagates through the fiber over a longer distance, right? So it will be directly proportional to the initial intensity of an optical signal. And it is written in terms of mathematical operations like dP by dL is proportional to minus P, where P here stands for the power of an optical signal. Capital L refers to the length of an optical fiber. Okay. And minus here it stands for, it is the decrease, the rate of decrease in the power. Right? And if I want to know let us take, what we do is we take this power p here, it becomes minus dp by p. Upon removing this proportionality limit by some constant, I use the constant as alpha again, equals to alpha into dl. Now let me assume that let p in and p out be the initial intensity, p in be the initial intensity with which the optical signal is latched, transmitted, sent, and P out be the intensity of an optical signal which is received at the receiving end as an output. Let capital L be the length of an optical fiber. So upon integrating this equation within the limits, here the limits of an optical, here the limits of an optical fibers are, limits of integration are P in and P out for the power. And the limits for the length is, we have taken it as 0 to L. Integral P in to P out minus dP by P equals to alpha into integral 0 to L into dl. Fine. Now, when I integrate, I'll get alpha into L, that is equals to integral of 1 by P is log P, and we have substituted the limits of the integration also, and here we have written it as minus log P out minus log P in minus of, it is in terms of log A minus log B, then it can be written as log A by B. Hence I write it as log of P out by P. My intention, my purpose is to obtain an expression for alpha. Hence I write in terms of alpha equals to, I take this L this side, it becomes minus 1 by L into log P out by P in. Basically we express in terms of Bell per kilometers. Right? Commercially, when I look at the attenuation coefficient alpha, it is usually expressed in terms of decibels per kilometer. When I want to express in terms of decibels per kilometer, I write alpha equals to minus 10 by L into log P out by P in. This is a very famous equation, quite important for us to know how much percentage of loss that has been suffered or occurred by an optical signal when it propagates through an optical fiber. Here, once again, I tell you, P in and P out are expressed in terms of watts, and capital L is expressed in terms of kilometers. Kilometers. Remember, usually we express the length in terms of meters, the SI unit. Whereas the case of optical fibers are concerned, they have been traveling, the optical signals are traveling over a longer distance, kilometers. Fine. Hence, I express L in terms of kilometers. This is an expression for attenuation coefficient, which is expressed in terms of power of an optical signal. Now, when I look at the one of the applications which has been included in our concept is the basics of point-to-point communication system. How the communication can be sent, can be received, can happen through an optical fiber. As since we say that optical fibers are meant for the optical communications. Right? So I need to transmit the signal, and I expect the same signal is received at the receiving end, right? For which I make use of a channel called optical fiber. Through that channel, the communications are made, the signals are transmitted from one end to the another end. Right? So here we have a block diagram. Okay, when a father wants to speak with her child, fine. Okay, so how the information can be sent through an optical fiber. The same information, what the father is speaking, the same information should be reached to his child. Fine. So here is a block diagram of point-to-point communication system. We say that whatever the information which we have as a voice of a telephone user will be in the form of analog electrical signals. Then these are converted into binary electrical signals with the help of CODAR. CODAR is a device which converts analog electrical signals into binary electrical signals. These binary electrical signals are later fed into the optical transmitter. Optical transmitter is a device which converts electrical signals into optical signals. You may ask a question, sir, can we send these electrical signals straight away to an optical fiber? No. Optical fiber only accepts optical signals. Optical signals can be obtained with the help of an optical transmitter, which converts binary electrical signals into optical signals. Later, we have a condition for ray propagation, as I mentioned in the earlier class, telling that All the optical signals cannot be propagated through an optical fiber. Only such optical signals which have the angle of acceptance lesser than theta naught, when theta naught can be accepted through an optical fiber, can be propagated through an optical fiber by undergoing total internal reflection. At the output of an optical fiber, and we have the optical signals. Optical signals cannot be sent as it is to his child. But what we have to do again, the reverse process of this has to be done. Once again, I need to convert these optical signals into binary electrical signals with the help of photodetector. Photodetector is a device which detects the optical signals and then converts them into electrical signals. Here we have the binary electrical signals again. These are once again decoded with the help of decoder to get back the electrical signals in the form of analog. Okay, so decoder is a device which converts binary electrical signals into analog electrical form. Okay, so hence the same information of this person is received at the receiving end. Right. So hence we say the information again in the form of analog electrical signals are obtained at the receiving end. This being the transmission part, this being the transmission part and this being the receiving part. Fine. At the receiving end, the child will going to receive the same voice of her father at the as he has spoken from the transmission end. Right. So this is one of the very basic aspects of the point-to-point communication system, how when signal is transmitted, in which forum the signal has been transmitted, in the same forum, the signal has to be reached and received at the receiving end. Right. And next we have several advantages and disadvantages of optical communication systems also. Right. Let us look out what are the advantages of these optical communication systems. And since they are meant for the transmission of optical signals, uh, the signals, the data, the information which they carry has to be received over a longer distance. And whenever these optical fibers can carry a large amount of information, either in digital or analog form. This is one of the advantages of optical communication system, telling that these optical fibers can carry a large amount of data or the information. And the material used for making optical fibers are silicon dioxide and plastic. And both these materials are easily available, readily available at a affordable rate at the low cost. Because of greater information carrying capacity by the optical fibers, the cost for the fiber would be lesser than that for a metallic cable. Whatever the metallic cables we use, they are a bit expensive in nature, and instead of them, we can make use of these optical fibers for the transmission of the optical signals. And also the last one, fibers are much easier to transport because of their lightweight and compactness. And this helps a lot for us to transfer the data or the information through the optical fiber for a longer distance. Now, when I look at the disadvantages found in terms of in the optical communication system using the optical fiber concept, here the very toughest task for us here is splicing. Splicing is a skillful task which, if not done precisely, the signal loss will be higher and results in a break in communication line. Right. And also we can observe whenever these fibers can be bent to circles of few centimeter radius, if they are not bent to still smaller radius, they may break and the loss would be considerable for smaller bends also. And to a limit extent, we can have the bend in the fiber. If I go further, there may be a loss that may happen, that may occur to the fiber. And fibers undergo expansion and contraction with the temperature variation that upset some critical alignments which lead to loss in signal power. And whenever there is a variation in the temperature, the fibers can undergo the expansion and contraction. During this process, the signals may escape from an optical fiber and becomes a loss. And that will be the greatest part for us, that to have a moderate temperature for the optical fibers are concerned. Right. So these are some of the aspects of optical fibers which we have discussed today. Okay. Thank you.